how to use some common rate law equations and draw potential energy diagrams. So what's the big deal? The big dealio? Well, I look at a couple ways. Things could happen really slowly, but that doesn't mean they're not important. Like, I don't know what the heck this hunk of stuff is here, but maybe it's really important. I don't know. And you'd have to know how long it's going to last. You can go out there and replace it, right? Maybe, you know, but more easier to probably relate to are pretty much every single type of drug that you take, whether it's for headache or a gut ache or high blood pressure or anti-tumor drugs. I mean, things are released in your bloodstream over time. You don't want all that stuff to hit at once. And then once it is released, what are the kinetics of it? How fast is it going to react? And what is the effect of, maybe I get more bang for the molecule if I can have more of it there, or less. You know, maybe they get in each other's way. So kinetics is a big deal with a lot of different reactions. And then to help you out is this whole idea of potential energy diagrams. It's kind of the same idea, to help you to get the most out of a reaction, or how to get to the end even faster or more with less energy. What a potential energy diagram is, now these are really complicated looking, and all they are is just potential energy maps. And you change where because if two reactants are going to react, don't they have to collide? Yeah, they got to collide. So as these molecules get closer and closer together, how does the energy change? What is their interaction? And you get some complicated curves, but if you can understand how the energy changes as these molecules approach each other from different angles, different geometries, and understand their reaction by drawing that energy out, you can figure out, oh, at this pressure would be better, this temperature, or this concentration, this catalyst, especially a catalyst. And you lower the energy, and you get things much more efficiently. For example, if there's you're making Coca-Cola and, I don't know, acid X tastes great, but it's really expensive. Well, if you're gonna make it, you want to make a lot of it, because all these reactions that hardly ever happen to 100%, but make a lot of it and low energy. So anyway, it's kind of ambiguous, but that's kind of where these are coming from. So let's start with some rate law equations, and all of these are derived. We're going to skip the math, but all of them are derived from something like this. You have one type of reactant, and it's simply pretty much just decomposing on you. It's falling apart, right? That's what it looks like to me, okay? And it can fall into one of three categories, and they say order: first order, second order, third order. Do you remember, Summer, where this order of a reaction is coming from? Oh, the overall order is this. Where did that come from? The exponents in the what law? Rate law. So they're not even going to give us the rate law. They're just going to tell us what the sum of all the exponents are. Either it's going to be 1, or it's going to be 2, or it's going to be 0. So they're going to tell us the overall order of the reaction, and depending on which one it is, that's the set of equations that we'll use. Okay. Now, these equations, there's a lot of variables in there. See if we can catch what they are. Maria, let's take a look at this first order equation. Do you recognize something in there? The K. What's that K? The rate constant, yeah. Okay. How about another one, Jasmine? You recognize any variables in there? The one I circled there. Like little t? Probably what? Not temperature. Usually they use what t's for temperature? Capital T. Time. It's supposed to be rate. How concentrations are changing over time. How concentrations are changing over time. That's a hint for the last two. AJ. There's 2 left. All right. There's this one. And then there's the bottom one. How about the one I circled? I'll give you a hint. Those brackets mean concentration. Yeah, well, of the reactant. Yeah, atom, molecule, whatever it is, of the reactant. concentration of that reactant. When? At, yeah, K is the rate constant. At a certain time. See, they have that little T down there? So that's the concentration of reactant A at time T or something, or a certain time, however you like to say it, right? After 50 seconds, little t is 50 seconds. Bracket A to T would be the concentration of A at 50 seconds. How about the bottom one, Mari? Now we've got this with a little 0 on it. It's a little 0. Looks like an O, but it's initial. So it would bracket A with a little 0 would be what? Initial concentration. Initial concentration. Initial concentration of reactant A. Okay. So we pretty much know what everything is, right, in all these variables. Oh, there's one left. How about over here, this T1/2 stuff? Anybody recognize this? Half-life. If the half, and this gives you equations on how to get what the half-life is. What would be the units of half-life? Seconds. It's time. It's the time for exactly how much of this reactant to disappear. Hint is half-life. Half. So the time for exactly half of it to disappear, that's the half-life. So you can get the half-life for all this stuff. So we kind of have an idea of what all these variables represent. That's important. The other thing that's important is the homework is going to give you, they're going to tell you which set to use. They're going to say first order, second order, zeroth order. Fine. So if they say zeroth order, and if you want to use this equation, pretty much they're all just plug and chug questions, right? You just got to plug the stuff in and solve for the unknown variable. Okay, so I say that's where we spend a lot of time here. Take a look at A. Which equation, let's erase all this stuff. Which equation am I plugging into? Does anyone see it? Recognize it? It's the first order, that first one. I'm plugging into this one. All I did is made up numbers, threw it all in there. In fact, it looks like, let's make sure we're reading this right. Lauren, you recognize the equation, right? Okay, let's make sure she's following it. What is the initial concentration of A that I made up? It'd be the bottom one. 3.9 times 10 negative 2. And the units? It's concentration, though. Molar, big M, right? Time will be seconds. Okay. No, concentration just big M. Concentration is big M all the time. So all I did is I just picked an equation. I just randomly threw in numbers. So it looks like here we're solving Cassandra for T. So what would you do first? We're going to need some light for these solar calculators. Okay, Cassandra, what would you do first to solve for T here? Okay, you could get rid of the negative 89, but for me, I would do that last because I'd find out what this natural log thing is first and then divide by the negative 89 to get my answer. Everybody agree? Okay, so try it. Now, the natural log, hopefully you found it on your calculator. It's a little ln. So I would take the 6.3 times 10 to the negative 3, divide it by the 3.9 times 10 to the negative 2, hit equals, then natural log. Right? Oh, I screwed up. There it is. Okay. So when you hit that natural log button, did you get negative 1.82? Yeah. Okay, but you're not done yet because you have to divide by negative 89. So your final answer, you'd have T is about 0.02. Right? Make sure you can get it. Okay. How about this next one? Here we're solving for, I guess, Albert, there's a whole bunch of English for B, whole bunch of English, and they're going to say in verbiage, what do they want you to find? What is that variable? Listen to Lauren. Initial concentration. They had a whole bunch of verbiage, and they told you, what's the initial concentration? They must have said first order again. Okay, so we plugged everything in, Eric, and now you got to solve for it. What would you do first? Oh, see, he wants to do that diagonal thing, right? He wants to bring the A0 up to the negative 35 and 5 and bring it down. What's wrong with doing it? You can't. Yeah. Yeah, this guy, they never put parentheses, but we probably should. All that's inside the natural log. So that won't work. Good idea, but won't work. Ramiro, got an idea? Oh, Maria remembers. How do you get rid of natural log? You have to raise everything to the little e power because they're inverse functions. So you raise this guy to the little e and raise this side to the little e. That's supposed to be an e. Right? And then when you do that, this stuff cancels, and you're just left with 2.49 times 10 to the negative 5 over A's initial concentration, right? Because the natural log's gone. Then the other side is going to be e to the negative, what the heck is 35 times 5? What is it? 175. Thank you very much. Okay? So now what would you do? Now we can do what Eric wanted to do, right? Now you can do what Eric wanted to do. Do the diagonal game. So we'll have 2.49 times 10 to the negative 5 all over e to the negative 175 will be my answer. But that's not much of an answer. You got to simplify it. So let's see if you can figure out how to do it. So first I'm going to put in the 2.49 times 10 to the negative 5 in the calculator. Put that in first. 2.49 exponent to negative 5. Right? So put that in first. And then divided by, push the divided by button. Now to get this exponential in the calculator, you have to push negative 175 first. So put in 175 and make it negative. And then you got to sit there and look on your calculator until you find the e to the x button. And it's yellow. So you have to push shift first. Shift, e to the x. Now that's, when you do that, that's e to the negative 175. So you got to hit equals yet. Hit equals, and that should be it. I got 2.5 times 10 to the 71.
Is it supposed to be that big?
No, it's just, I made up stupid numbers. Right? I didn't really care. I'm just playing with math. I don't really care about whether they make conceptual sense or not. But yeah, that one doesn't, right? How could initial concentration be 10 to the 71? Doesn't even make sense. Okay. Make sense? Everyone get it? All right. Let's try another one of these. C. Monica, it looks here like in all this verbiage in the problem, all the English, they ended up saying, hey, find what? Yeah, it's gonna. Yeah, they must have said second order, 'cause it's the second order equation. But they wanted you to find what? Concentration at time t. They wanted you to find that, so that's what she's solving for. Okay. So Vanessa, what would you do first here? Okay. She wants to do the 1 over 2.4 times 10 negative 4. Then do what? So she wants to do this first. I like that because I can do it all. The way she's doing it, I can do it all in the calculator without writing anything down. So do this part first. Then what? Plus 18 times 12. Then hit equals, right? So then you'll have a number on this side. And then you pretty much just have to flip both sides of the reaction. Flip both sides of the equation. Right? You flip this side and you flip this side. Or you can do the diagonal thing that Eric was talking about. Same thing. You're going to have to take 1 divided by that number to get the concentration A at time t. Right? So do the... I'm going to do the 2.4 times 10 to the negative 4. And push the 1 over x button. Got to find it here. There it is. Shift. Okay. And then plus 12 times 18. Hit equals. The calculator knows it has to do multiplication before addition, so that's why it works great. So plus 12 times 18, hit equals, and then I have to take that number, bring it down here. A at time t goes up on top. So it's pretty much just 1 over. And then you get about 2.28 times 10 to the negative 4. Okay. Victoria, you get that? Okay. Okay. I'm going to write an answer down for this one, and then you can try the next one. Times 2.2 times 10 to the negative 3. Make sure that's right. Yeah. Okay, so this is just for practice for you to do at home. You can try that one. And you should get that answer for that one. Okay? You have to raise both sides to the e power again. How to do C?
Yeah.
Okay. What I did first is I took, 1 divide, or just I put in 2.4 times 10 to the negative 4 and push the 1 over x button. Or just take 1 divided by 2.4 times 10 to the negative 4. And then do plus 12 times 18, hit equals, and then just push the 1 over x button, because that would flip both sides. Okay, and we'll get into these a lot more and give you some more practice. But let's see if we can answer some of these questions here. Brandy, my initial concentration is 2 molar. Half-life is 5 seconds. What is the concentration of A? I guess you have a little T down there. What is the concentration of A after 5 seconds? What would you say? So the half-life is 5 seconds. Initial concentration is 2 molar. 5 seconds has gone by. No, they want to know how much is left. So exact 1 half-life, so that means half of it had to disappear on you. So you'd be left with, not seconds, right? How much? Anyone see what I'm driving at? Right? Your initial concentration was 2 molar, and 1 half-life went by. So you'd multiply it by a half, essentially, right? You end up with 1 molar. You see that? See what I'm driving at, Brandy? Okay. Now 20 seconds has gone by. Summer, 20 seconds has gone by. How many half-lives is that? 4. So I'm going to follow the exact same idea. 4 half-lives went by. So I'm going to multiply a half 4 times. Well, then times the initial concentration. I don't know, whatever you get, right? For the third one, 30 seconds, 6 half-lives. So I guess instead of writing 1/2 6 times, I could write 1/2 to the 6th power times 2 molar. And then whatever I get will be my answer. Okay. Just however many half-lives go by, just write down a half that many times. That's the trick to doing those. Okay, before we jump into, this is the meat and potatoes of what we're after, right? This type of question, where I give you all the rate constants and everything and ask for initial concentration or something. We need to do this first. Talk about how to sketch a general endothermic or exothermic potential energy diagram. Right? How does the energy change as reactants go to products? So down on the bottom, you could write time, but they don't like that. They want you to use the word reaction coordinate, because what the computer does is it puts all the nuclei of these reactants in different locations, and then it calculates their energy. Changes their location, probably makes them a little bit closer, calculates their energy closer, right, as A and B collide. So you're starting, and then y-axis is potential energy. Okay. Now if it's endothermic, Jasmine, does that meant that what? Heat was a reactant or heat was a product? Which one did it mean? It was a reactant, because endothermic, it's a heat is reacting, everything's getting colder, right? Okay, so if heat is a reactant, that means you're going to end up here. You're going to start out way down here, because heat's a reactant, right? You're going to have these reactants, they're going to suck up some heat and end up way up there. So whatever the reactants are, you write them here. In our case, it's just A and B, but whatever they were, you'd write them down there. And whatever the products are, you write it up there. And they don't want you to draw a straight line between the two. They want you to draw a little hump. Okay. They want you to draw a little hump. And then they want you to label a couple things. One is the enthalpy. What symbol was the change in enthalpy? Delta H. And all you do is you find out where the reactants are and where the products are. Wherever they're at, draw an arrow between them. That's your delta H. And there's one other thing they want us to label, and that's the energy of activation. The energy of activation. And that's a lot to write. So they abbreviate it EA. And the energy of activation is, okay, I'm a reactant. Just exactly how much energy do I need to turn into a product? So you start wherever the reactants are. All right, and you're going to have to draw it all the way to the top of that hump. Because that's how much energy it needs. What catalysts, I don't know, catalysts might be a little more than you need to know, but catalysts end up lowering that hump is all. But okay, so that's how you draw it for, that's how you draw a potential energy diagram for an endothermic reaction. Do the same thing now for a exothermic reaction. Well, we have to label our stuff. We have potential energy. We have reaction coordinate. But now heat is a product. So you got to start out really high. And you're going to end up really low, because now you're giving off all this energy. Okay. So write the reactants, whatever they were. Write the products, whatever they were. Don't draw a straight line between them. Draw a hump. And stick in your delta H. Stick in your energy of activation. And remember, delta H is just between the reactants and the products. Energy of activation is the energy the reactants have to overcome to get converted to products. All right. So hopefully you made this one your delta H. And your energy of activation is just a little guy. Right? That's your energy of activation. Okay. I think the homework has you do at least one of those. So all you care about is whether it's an endothermic or exothermic reaction, and then just kind of label things appropriately. Okay.
Why is this one energy of activation? Why is it like smaller?
Oh, because all energy of activation is just the energy needed for the reactants to get converted to products. So if you're starting out right here, this is all you need is just that height,
So,
and then you're done. So it's just the energy that they need to overcome
just to get to that.
to get converted to a product. Over here, dang, they have to start way down here, go all the way up over this hump, and back down. So the energy of activation is a lot bigger. So wherever you start out, they're just starting out higher for exothermic reaction. Okay, here we go. We got some time that we can work on these. So I'd like to approach this a little bit differently, Jasmine. I mean, because right off the bat, they say it's what order? Reaction, second. So we could jump right to the equation, but instead I want to ask you, AJ, to give me a variable and the number that goes along with it. All right, you recognize anything in there, and give me its variable. Okay. And what's the symbol for it? Yeah. 0.225. Oh, hold it. No, it's not that one. Yeah, it's the 0.293. Okay. Now keep going, Mari. How about another variable and its number? The rate constant is 0.225. And what's the symbol for it? K. Okay. Keep going, Lauren. No, not. They didn't say anything about half-life.
That's not measured in seconds.
Yeah, but there's something else measured in seconds. Time. And what symbol is that?
35.4.
Well, what's the symbol?
The lowercase t.
Yeah, just that little t, right? Okay. Now we have everything. Cassandra, we just have to write the symbol that we're looking for. Something equals question mark.
Concentration of
Yeah.
the base drug.
There you go. Okay. So, like Jasmine said, it's second order. Find the right second order equation. Substitute everything in. Solve for the concentration of A at time t. We'll try it. See if you can get it to work. What'd you get, Eric? Negative second? 8.8 times 10 negative second. Would anybody else get this?
Yes.
Really? What units? You lose a point. Big M. Several folks got this. So I bet you it's right. Okay. Give it a shot. Now we've got 1, 2, oh, we've got a bunch, right? We can go to the boards or you can stay where you're at. Is there a preference? Preference. People don't seem too eager, right? Let's stay where you're at then, right? Unless some. Yeah, summer camp. I'm not gonna stop you. Right? Okay. I think we should get through definitely 65 because I think one of these, yeah, it does. It throws a curveball. Why don't we just start with this one that throws a curveball at us, right? Right? Let's start with 65. Let's do the curveball one. See if you can figure out this one. You're not sure, just ask. What is the half-life?
Is that all?
Well, if it's first order,
First order.
it has to be this one.
And
All you need is K. You can find it. What are you going to do, Vanessa?
Because they're first order.
First order, so it has to be one of these two.
We're looking for half-life hours.
Yep. Except when you do half-life, you're going to find it in what units? You could look at your K.
Yeah.
Seconds. So you just have to convert to hours, right? So go ahead and get your half-life, and then it'll be in seconds, and then it's convert it to hours. So do you see how to do the first part? Find your it's first order, so the half-life 0.693 over K. Is that right? Did I remember that right? Okay. But they want the half-life in what units? Hours. Who cares? Don't worry about it. Get it in seconds first, because that's what K is in, and then convert to hours. Right? So go ahead and get it in seconds, and then convert to hours. Because if you try to convert to hours first, you might screw up because seconds is in the denominator. It's not as straightforward. So I would go ahead and get your half-life. In seconds, then convert to hours. So you divided that by how much? How many seconds in an hour? 3,600, right? Yeah, that looks right. 3,600 hours. Mm-hmm. About 96 hours. Looks right. Summer got about 96 hours. Did you? Okay. A lot of folks are getting like 96 hours. Take a look at Summer. She got it, right? She got, first she used this one. Half-life is 0.693 over K. So she got her half-life to be 346,500 seconds. And then you got to convert the seconds into hours, so she divided by 60 twice. Man, we should all be at the boards, right, Summer? Jeez.
I find it easier.
But that's not the whole question, though. Look at it. You got to keep going.
I don't know what to do.
Oh. Okay. Hey, what is the question? They want to know how many hours would be required for the initial concentration to decrease to. So what type of equation what are they looking for in the second part? They're looking for what variable?
For hours, don't
Yeah, they're looking for hours, but what variable is that in the equation? That's
Oh, the T?
that's the t. They're after the t.
Where did you get the...
Okay. The second part, yeah, is good. Okay, the second part, what symbol are we looking for? What symbol are we going to be solving for? We're going to be solving for t in the second part, right? Okay. It might help us to write the equation. What equation are we going to be using? It's first order, right? So what is the equation? Over the initial equals what? Okay. So there's a couple ways we can do this. One is when it says 25% left, what could you do? Is the
Multiply by 0.2.
do they even tell us what the initial was? All right. Okay. What's that? Oh, I just said it right down. Okay. Yeah, we're very, very close. Okay, think of it this way. If you had, if half of it was there, if it was 50%, right? You would write this, right? If it was 50%, wouldn't you write that? Does that make sense to you? If you have 50%, at time t is 50%, that'd be 0.5 A0. Okay, now this is the trick. Once you see the trick, it won't be so bad. So if let's just add 50%, right, into this list. Let's add 50%, okay? So what we're going to do is A at time t is 0.5 A0. All right, let's just do the 50% one. So you'd have a natural log of 0.5 A0, because that's what concentration of A at time t is. Didn't we just say that? So I'm just substituting it. The bottom is A0. It's just going to cancel out. That's why they didn't even tell us what the initial concentration is, because it just cancels out on you. So you just take the natural log of 0.5, divide it by our rate constant, and we'll get our t. Oh, you got to convert to hours. Did they want hours? Yeah, they wanted it in hours. Okay. So let's do one of the ones they actually asked for. They actually asked for 25% left. Yeah, it's 25% left. It would be 0.25. 0.25 A0, right? That'd be 1/2 left. What's that? Okay, we copied this from our equation. Okay, and then what we did is the concentration of A at time t, if we're shooting for 50%, that has to, then this equation has to be true. That the concentration of A at time t is 1/2 of the initial. Do you see that? So if they want 50%, you put in a 0.5. If they want 12.5%, you put in a 0.125. If they want a 6.25%, you put in a 0.0625. But either way, whatever you put in for the concentration A at time t, you always have it times an A0, but you have an A0 down the bottom. See, he's going to just cancel out on you. Okay. You end up with a natural log of 0.5 equals to negative kt. You know what your k is. Solve for t. Get them in hours. Okay, so we're about out of time. But combine, I'll be glad to help you out with this. Okay. So this is okay. I think you can do it. But come by.